Hi, in this video, we're going to check what we have learned about electron configuration and orbital diagram and valence electron to help us understand about the chemical property of the different families or the different groups on the periodic table. So we see the elements in the same group tend to behave chemically similar to each other. And we see the reason why in a little bit. Let's now go over element in the group 1 first. So we can see that the electron configuration for element in the group 1 will then be ns1, where n here is the period number. So if the element is on the first period, it'd be 1s1, versus for element on the second period, it'd be 2s1, and then on the third period, 3s1, and so on. But then this is the generic format of its electron configuration. And we can see that it actually have one valence electron. Now this one valence electron right here can ionize easily, in which that the atom would be given off its electron to become the positive charge. And we can see that in this case right here, group 1 elements are metal. And because they are metal, they like to give up electron. And in this case right here, they have one valence electron. So therefore we can see that the group 1 element can give away one electron easily to become then the +1 cation. Why do they want to give up one electron? The answer is so that because they want to have electron configuration that is similar to the noble gases. Because we see that noble gases are elements that are very, very stable. So all elements want to have the electron configuration that is similar to the noble gases. And we call that terminology right here, isoelectronic. So all elements want to be isoelectronic to the noble gases. So what does this term isoelectronics mean? Iso here means the same. And electronic here refer to the electron configuration. So all elements want to have electron configuration that is similar to the noble gases. And if we were to look at the periodic table, we could then see that group 1 element have one electron more compared to the noble gas from the previous row. So therefore, they all want to give one electron, because when they give one electron away, they now will have the electron configuration similar to the noble gases. For an example, let's take sodium. The electron configuration of sodium is that they have the neon core followed by 3s1. So in this case, it has one valence electron. And in fact, they have one extra electron more compared to neon. And therefore, to become similar to neon, or to become isoelectronic to neon, sodium would then want to give this one electron away. And when an atom gives one electron away, it then becomes +1. And now that is all this is the electron that now it has given up. And now the electron configuration of this sodium ion would then be as follows. Neon followed by 3s0. So the one electron in this 3s right here have now given up already, so we have 0 electron remaining. So in fact, we don't even have to put this 3s right here, but we can simply just ignore it, because we only care about orbitals that have electron in them, or we simply can just say neon. So as you can see, the electron configuration of this sodium cation is now similar to the electron configuration of neon, and that makes it stable. So this is the reason why that the group 1 metal would like to give one electron away. And we will then find this to be true for all elements in the group 1. And now, let's do an example of group 2 element, the earth metal. So the electron configuration for them, or the generic format, is ns2, where n is again the period number. So in this case, they have 2 valence electrons. And because they're still metal, and we know that metal would like to give electron away. And in this case, because they have 2 valence electrons, therefore they can give away those 2 valence electrons. And that's why they can form the +2 ion. So that's the types of cations that group 2 element would like to form. For an example, let's take a look at magnesium. The electron configuration of magnesium is that they have the neon core followed by 3s2. So it has 2 valent electrons. In chemical reaction, magnesium would then want to give 2 electrons away to become magnesium plus 2. And the reason why, because that it like to give 2 electrons away, that it have 2 electrons more compared to neon. So therefore, I like to give away 2 electrons so it can become isoelectronic to neon. And now, once it have formed this magnesium plus 2, its electron configuration would now be neon followed by 3s0. So there's no more electron left in this 3s. And we can omit that and simply just write neon. So now we can see the electron configuration is similar to neon. So magnesium plus 2 and sodium plus 1 have similar electron configuration to the neon. And when they have the electron configuration similar to neon, it now becomes unstable. So all elements behave so that way they would have the same electron configuration as the noble gases. And in the case of metal would like to give electron away to become isoelectronic to the noble gases. And now, let's now move on to the group 17 element, the halogen. The electron configuration of the halogen will be ns2 and p5, where N is again the period number. So in this case right here, they have 7 valent electrons. If we were to look on the periodic table, we would then see that the halogen are group 17, which is one group away from the group 18. So they basically have 1 electron less compared to the group 18 of the noble gases. And therefore in chemical reaction, they would like to gain an electron, because the best way for them to have electron configuration similar to the noble gases is by gaining 1 electron. Now, they only want to gain 1 electron, not 2, not 3, but then just 1, because group 17 element have 1 electron less compared to the noble gases. The noble gases has an octet of electron, and in this case, this have 7. So the best way for it to become 8 have an octet of valent electron is simply by gaining 1 electron. So therefore, all group 17 elements tend to form the -1 anion in chemical reaction. For an example, let's say iodine. The electron configuration of iodine is that it have the krypton core followed by 5s2 and 4d10 and 5p5. So when we add all of the valent electrons together, then now it would have 2 here and 5 here. That make up the 7 valent electron. And in chemical reaction, then iodine like to gain 1 electron, and that one it becomes the -1 anion. And the electron configuration of this iodine negative right here will then be as follows: Kr followed by 5s2, 4d10, and now 5p6. So it's really important that we understand when an atom gains an electron, where it will now put the electron. So in this case right here, this 5p right here is the highest energy orbital that not being filled with electron right now. So if we were to have actual electron, will be putting this electron in this 5p orbital. And therefore, this changes from 5p5 to now 5p6. So that's something we expect students to be able to understand, that when an atom gains an electron or multiple electrons, we need to be able to figure out where that electron would go. And this then becomes the electron configuration of this iodine -1. And now, this electron configuration right here is now actually similar to the electron configuration of xenon. So iodine -1 is now isoelectronic to xenon. So have similar electron configuration to xenon now. And this is basically the driving force for the chemical reactivity of the different groups, that all groups, they want to have electron configuration similar to the noble gases. For metal, by losing electron, that's how they can become isoelectronic to noble gases. Versus for non-metal, they tend to gain electron. So group 17 would like to gain 1 more electron. Group 16 are 2 electrons away from having the same amount of electron as the noble gases. So that's why they like to gain 2 valence electron. And this is why the group 16 element, they form -2 anion, versus the group 17, they form -1 anion. Okay. And now let's discuss the noble gases. So the noble gases, so this is the general format of the electron configuration, and they have 8 valence electron. And when they have the 8 valence electron, then the orbital, or all of the orbital, are then completely filled, and now they have 8 electrons in them. And we call this having an octet of electron. And this makes them especially stable right here. So that is the electron configuration, and how we explain the fact that the noble gases are not reactive, because they already have the most stable electron configuration. And lastly, let's now discuss the hydrogen. So hydrogen belongs to the group 1. All elements on the group 1 are basically metal, but except for hydrogen, hydrogen is on group 1. However, it is a non-metal. And because of it, hydrogen tend to have chemical behavior of group 1, and it also have the chemical reactivity of the group 17 as well. Because when it is non-metal, it actually been classified into group 17. And so the electron configuration of hydrogen in 1s1 has 1 valence electron. It can give up this 1 electron right here easily to form the +1 ion, just like all other elements from group 1. It can also gain 1 electron to also acquire the helium electron configuration as well, and becoming the -1. Because hydrogen is 1 electron away from being similar to helium, and of all of the noble gases, helium is the only one that has only 2 valence electrons, versus everything else have 8 valence electrons. So because hydrogen now have 1 valence electron, if it can gain another, it will be able to become isoelectronic to neon. So this is why that hydrogen can do both. So let's write a few things about this. So in this case right here, hydrogen, that is the electron configuration. It can gain an electron to now become H-1, and now its electron configuration then become 1s2, or isoelectronic to now helium. So that explains that chemical reactivity of hydrogen. Hydrogen, we observe that it can also form cation as well, in which that it gives up 1 electron to form the hydrogen ion, and now plus the 1 electron. So in this case right here, this electron configuration is now 1s0, and this is because so this property right here is because it belongs to the group 1, which they tend to give their 1 electron away. So that is the chemical reactivity of hydrogen, and just like all of these groups right here, and how understanding about the electron configuration and valence electron help us determine and understand the chemical reactivities of elements from the different groups.